we have a theory for gravity, and we have one from quantum physics, but we don't really have one from quantum gravity. And one of the problems, as I see it, is gravity is extremely weak force, where quantum physics, we have a lot of experiments here on Earth that we can easily explore the quantum world. Physicists like you are exploring the aspects of quantum gravity by looking at black holes. Can you explain why black holes is the place to perform these Gedanken experiments?
Yeah, well, first, I fully agree with you that, I mean, I think the major challenge for theoretical physics in this century is to come up with a quantum theory of gravity. We have general relativity, which is an extremely successful classical theory of gravity and explains, well, a remarkable array of things from solar system experiments to gravitational waves to black hole coalescences observed by LIGO. So there's ample reason to think it's correct, and also the expansion of the universe and properties of cosmology. So that's incredibly successful. We have incredibly successful quantum theory of fields that basically explains all phenomena observed in accelerators, but we haven't been able to put them together. I mean, gravity clearly also must satisfy principles of quantum mechanics, and the standard model of field theory is certainly incomplete without including gravity. So, I mean, one of the things one could approach this by trying to write down a grand theory that does everything, but another way of approaching this issue is to try to look for phenomena where both gravity and quantum mechanics play a role, and analyze what's going on there and try to get some insight into the kinds of features that quantum gravity has. So I haven't been attempting, I mean, if I had some good ideas, I would attempt, but I haven't been attempting to write down a grand theory of quantum gravity. I don't know how to do that, but you know, I do know a little bit about black holes. I do know a bit about quantum field theory and quantum mechanics, and thinking about situations where both of them play an important role. Well, then if it's certainly interesting to do.
Yeah. So if you're going into the universe and look at where a quantum gravity theory would actually play a role, or where it could show up, you know, that would be maybe the Big Bang, and then you would probably have black holes. Do you have anywhere else in the universe where you're thinking we are seeing something where we need quantum gravity to explain it, or are we only in these extreme you know, cases of black holes and Big Bang where it would play a role?
Yeah, well, I mean, so classical general relativity predicts the presence of singularities, and the primary ones are the ones you mentioned, the singularity at the origin of the universe, the Big Bang, and it also predicts singularities within black holes. So those singularities are clearly places where one would expect classical general relativity to break down, and where quantum phenomena would play a role, quantum phenomena in gravity. But, you know, there may be much smaller and more subtle effects that, you know, occur in less extreme situations. You know, but there's no obvious, well, I mean, an interesting thing to do is to look at phenomena where both quantum theory and gravity play a role. We, you know, have a good idea of what, if space-time is nearly flat and the deviations from flatness, the effects of gravity, in other words, are very small, then one could make an approximate quantum theory.
So that kind of brings
gravity,
you to, yeah, exactly.
And see what that predicts. Yeah. And there will be quantum effects that could, in principle, be seen, but they're probably not going to tell us a lot about the most interesting things of, you know, like what really happened at the Big Bang, or what is really going on at the singularity inside a black hole, and, you know, other things related to that, but they'll give us, you know, some indications of what quantum theory mixed with gravity is.
So what you're saying is that right now we don't, as everybody knows, we don't have a theory for quantum gravity, but we are still able to mix the two things in the weak regime, say, you know, quantum physics in, you know, weakly curved spacetime. So if we consider that problem, then I know that has been worked out very close to black holes, right? The horizon of black holes. And that, you know, for many people think that black holes are completely black, but that's not really the case when you take into account this coupling of the quantum physics with the curved space-time. Could you expand on that? Like if you think about Hawking radiation and some of the other things that brings us to black holes as laboratories.
Yeah, well, one of the, I think, most interesting developments in physics, but certainly in general gravitational physics in the last 50 years, was Hawking's discovery that there would be spontaneous particle creation outside of a black hole. So that's not really violating the idea of a black hole. There's still nothing that is coming out of the black hole itself.
Could you describe that in, you know, more simple terms, how you could think about that?
Yeah, well, there are particles being created near the horizon, but outside of the horizon of the black hole. So in the observable to us part of space-time, and some of those particles can then escape and propagate out to us. That's remarkable in itself, but even more remarkable is that the nature of the radiation that comes out to us from this particle creation is just like the kind of radiation that you'd get from a hot body. Well, the black hole is very cold, but the nature of the radiation is the kind of radiation that you get in what's called thermal equilibrium, and that tied together a very close relationship between laws of black hole physics and laws of thermodynamics.
So
it's that kind of thing, I think, is really giving us some major clues as to what the nature of black holes in a quantum theory of gravity must be like.
So what actually came first, like the thermodynamics picture of the black holes? Didn't, like, people thought about this before Hawking made his
yes, it's quite remarkable.
Was it at the same time, or?
Really, several years before Hawking's discovery, it was found that there were certain laws obeyed by black holes that you derive using Einstein's equation of general relativity, so anything like thermodynamics or statistical physics. But these laws had a mathematical character that was very analogous to laws of thermodynamics. So there was a paper by, in fact, Bardeen, Carter, and Hawking a couple of years before Hawking made this discovery, you know, entitled, I think, The 4 Laws of Black Hole Mechanics, that developed this analogy. And they say explicitly in the paper, this is just an analogy, because black holes don't really have a temperature, or it would be absolute zero, and so on. Then a couple of years later...
What was the 4 laws that they put forward? Did they put them in simple...
well, they're the analogs of the 0th law of thermodynamics and the 1st, 2nd, and 3rd laws of thermodynamics. So that's how their counting worked. But then Hawking discovered that, in fact, black holes really do have a temperature that, you know, the role of which was played by the quantity they had identified as being analogous to temperature in the mathematical laws.
It does really seem like it's, you know, just an application of still gravity and quantum physics. and you're
Yeah.
looking at the interplay. But does it give us any insight into a possible quantum gravity model, or are there other ways of exploring this problem than going from the weak field limit and trying to extrapolate to the strong limit, or
Well,
what are the different approaches?
Okay, I mean, we're of course in the regime of a black hole, so that isn't really a weak field limit. The deviation from a classical black hole solution is assumed to be small, so that's the sort of weakness that allows one to do a quantum mechanical treatment of this deviation from the classical black hole. Well, I think that's, we've got the clues, right? We haven't solved the mystery, I think is the point. But, it's a great thing that we have clues to work with. What that really means for black holes, what the nature of black holes is and will be in a fully quantum theory of gravity remains, on the table for us and the next generations to explore, and maybe somebody will come up with a complete theory that will account for everything, and then we'll see that, of course, black holes obey laws of thermodynamics, and that will be taught in elementary physics. But right now, that
suddenly everybody knows. Of course, that's the
that's right.
That's how
but now
goes.
It's just a very intriguing clue.
So your own work, some of the recent work that you have been doing is how these black holes, interact with the surrounding universe.
Yeah.
Can you tell a little bit about how that acts in relation to the work that we just were talking about? Is that a next step, or is it different views on the same problem? Or
well, I think it's another clue. I mean, not. I wouldn't put it in the same category as the clue that Hawking gave us with the particle creation, but yeah, this work is essentially showing that if you create a quantum superposition, that would take a little while to explain, the presence of a black hole will make it impossible to later do an interference experiment with a successful interference experiment with the two components of the superposition that you've created. It's as though, and it's in some sense literally true, really, that the black hole is making an observation of your quantum mechanical system, and it's thereby, again, the technical term is decohering the system in much the same way as if I created a superposition and you came in and made a measurement of whether the particle was here or here, that would decohere the superposition. But a black hole is capable of doing the same thing.
Is it only black holes, or like I can imagine other things that are also
other things, everything that interacts and
over time would
causes,
be able to,
well, anything that causes dissipation would also, experimental, I mean, real experimentalists as opposed to Gedanken experimentalists, which is what I am, very much have to isolate their system. If they're doing a quantum mechanical experiment, they have to isolate it from the environment to prevent the environment from performing decoherence. But the decoherence that the black holes do is a kind of very intriguing, simple, and calculable decoherence that, well, I certainly find quite intriguing. Black holes are by no means unique in being able to do the decoherence, but I would have, before this recent work, would have thought of black holes as kind of completely inert objects that wouldn't register any information about what you're doing in your laboratory experiment and would not play any role in decohering your quantum system.
So if we're talking about black holes, which are very astrophysical objects around us, and we see them in gravitational waves and so forth. if we are, thinking about other very extreme phases in our universe, as we talked about the Big Bang, are there phases during the Big Bang where the things that we just talked about, are created or manifest as things that are, growing up to be part of the universe that we see today? Like, I mean, if we think about in inflation, like one of the, standard way of thinking about this, that you have these quantum fluctuations, that they're blown up, or very short, very rapid expansion. Some of the things that you're talking about here, do they blow up in the same way and manifest as some of the things that we can see today, or?
Yeah, well, in fact, I mean, the phenomena that occurs in inflation, is actually quite analogous to the phenomena that occurs in the Hawking effect with particle creation by black holes. They're not the same thing, but there is considerable similarity in the way there's effectively particle creation that goes on, in this case from the expansion of the universe, in the black hole case from the behavior of the quantum fields near the horizon of a black hole. So again, that is probing some quantum phenomena in a gravitational context. The expanding universe is very much a gravitational context. It's not, although inflation would be probing the extremely early universe compared to other things we can observe. We can observe, microwave background. We can observe, helium synthesis, things like that, or the effects, the helium that was synthesized in the very early universe. The inflationary picture is going back much, much further, but it's not getting us all the way back to the Big Bang and telling us that, about what the quantum gravity nature of the singularity is, or at least it's not. Maybe it will be telling us that, and maybe, that's another clue, really, but right now it remains a clue rather than it implies that the Big Bang must have been like this or like that.
So if we're taking out, a bigger view here, then for many of the other things like quantum physics and general relativity, there has always been a component of observations, right? Einstein's theories, you can easily observe, the bending of light, or by the sun first, the bending of the starlight around the sun, and you can now see it in gravitational waves and stuff like that. So this quantum gravity, some of the things that you are talking about, will they in the far future only live in these Gedanken experiments, or do you see potential ways of observing this, or lucky observations, or maybe something in collision of black holes? Do you hope that will happen, or you only see a path that is keep thinking about these experiments? Yeah,
well, the collision of black holes, that sounds like something, but again, the singularities are deep within the black holes.
Yeah, exactly.
And even during a collision of black holes, there will be some very dramatic and interesting things going on with the singularities for sure, but it's all hidden from us.
We don't
still.
see it. Yeah.
So that's not likely to provide us, unless general relativity is wrong.
You have modifications, for example, that will point us in another direction. Yeah, exactly.
Right, but there are tabletop real experiments that people are certainly talking about doing, and might well be done, in the next 5 years or 10 years, where, again, you have quantum mechanical, what would normally be described as quantum mechanical systems, but they are interacting gravitationally, and the gravitational interaction is, well, again, the terminology used is mediating entanglement between the systems. These systems are getting correlated in a quantum mechanical way through the interaction of gravity. And so that's something that could be done as a real experiment, you know, in the not too distant future, and that would verify the quantum nature of gravity. If you had a purely classical theory of gravity, I mean, making a purely classical theory of gravity that couples to quantum mechanical systems is a, you know, you have to strain to make up such a theory, but one can do that, and that would rule out these experiments if they're successful and the outcomes are what I think everybody would expect. That would show that gravity has to have a quantum nature to it. So that could be shown. I don't think that's, well, of course, if gravity doesn't have a quantum nature, that's going to be a major development, and that's going to cause a lot of rethinking. But if it does have a quantum nature, as everyone thinks, it's not going to tell us very much about the quantum nature, because this is very weak field where we believe we already have a good approximate description of the quantum phenomena that gravity might, you know, do. What we're completely lacking is a description of what's going on near singularities and things like that. And these tabletop experiments, I don't think will help at all in that regard.
So I don't know if it's even a relevant question, but do we even do we expect that gravity and quantum physics simply cannot, you know, be mixed? Is there? Could we ask if there is, you know, a theory of quantum gravity? Are we looking for something that might not even be there? Do we even need it in terms of, you know, describing the, you know, production of the large-scale structures of our universe, the particles that we are seeing? Are we just hoping that there would be something, or?
Well, I mean, I think
it looks like we're doing fine without it.
I mean, going back to what I said at the very beginning, we have a very good classical theory of gravity, but it interacts with quantum systems, and it is essentially inconceivable that gravity itself could not have quantum properties. And we have an excellent, you know, quantum field theory model of basically everything except gravity, everything we've seen, but, you know, gravity has to be included in that. So there has to be some theory that is merging the two in some way. Now, maybe that theory is going to look very different from classical general relativity and very different from quantum field theory as we know it. I mean, that is a genuine possibility. I mean, but, you know, we'll only find out when we get there.